Today in the workshop we'll be discussing troubleshooting, what to do when your project doesn't work. I'll show you how to diagnose and repair both hardware and software problems. We're staying out of trouble today, so welcome to the workshop. Well, hello and welcome to the workshop, and today I've got a bit of a different episode for you. It's different in the way that I'm not going to be explaining the use of a new component, and although we are going to build a project, the reason we're going to build it is so we can break it. And why I'm doing this is because today we are going to talk about a very important skill, and that is troubleshooting, what to do when the stuff doesn't work. Now, I'm sure everybody has experienced this. I know I have many times. I've put something together following something I saw maybe on a video or on an article, or maybe something I got out of GitHub, or maybe just something I've conceived myself, and I figured, hey, this thing's going to work, it's going to be wonderful. I put it together and it doesn't work. So what do you do at that point? Well, what you don't do is panic, because that isn't going to resolve anything. What you should do is troubleshooting. Now, troubleshooting is actually a process. It's a process of going step by step to figure out what is working, what isn't working, and eventually it will lead you to what the problem is. Now, I want to be clear that what I'm talking about today is troubleshooting projects that we build ourselves. And so I'm not talking about troubleshooting problems that you would have, let's say, with your television or with your toaster oven or something like that. Although a lot of the principles that we're using apply to troubleshooting everything, including your car. But we are going to focus on troubleshooting stuff that we build. Now, one difficulty in troubleshooting the projects we make is that we make use of a lot of things like Arduinos, Raspberry Pis, NVIDIA Jetsons, and because of that, sometimes we aren't even certain whether we might have a hardware problem, such as a bad component or a wiring error, or maybe it's a software problem. Maybe there's something that's wrong with our code. And I'm going to cover both of those, and also how to try to determine which is which. And I'm also going to show you how, because we are using microcontrollers and microcomputers, we can use them to our advantage when we are troubleshooting. So it's a two-way street. Another thing is that some of you may be thinking, oh yes, but you're in a workshop, you've got oscilloscopes, signal generators, all kinds of wonderful test equipments. What do I do if I don't have that? Well, actually, you do not need to have that. It is, of course, something wonderful to have, but you can do basic troubleshooting and solve most problems with just a multimeter. I'm going to show you another piece of test equipment that you might want to pick up that'll set you back all of maybe $25, and that you could even build yourself, but it's optional. A multimeter would be really all you would need for the hardware troubleshooting, and as for the software troubleshooting, all that you are going to need is your brain. So let's start off by taking a look at what a troubleshooting process involves. I'm going to show you a troubleshooting process that is kind of a standard. It's called the CompTIA process, and it's a standard certification process, and we'll kind of build upon that to troubleshoot our stuff. After that, I'm going to build a circuit, and then I'm intentionally going to break the project, and we will see how we could troubleshoot that. So let's get going. CompTIA is an international computer technician certification organization, and they've developed a 6-step process for troubleshooting that they teach to their technicians, and we can learn from it. Now, the first step in the process is simply to identify the problem. I say simply, but actually, in some cases, people do not do this correctly. They only identify one of the symptoms of the problem and not all of them. You need to thoroughly look at the problem and see what is working and what is not working. The second step is to establish a theory of probable cause. I'll use a car as an example. If the engine won't start, it's very unlikely that it's being caused by poor tire pressure. Similarly, in an Arduino circuit, you can establish whether the cause is hardware or software, and I will be showing you in this video how we can determine that. The third step is to test the theory to determine the cause. Again, you'll have to establish the theory and then go through and run a test. If it is a hardware problem, you can test with test equipment or by substituting components. If it is a software problem, you can test by injecting different code into your code, changing the value of variables, or monitoring things with your serial monitor. Again, we will go over those steps in this video. The fourth step is to establish a plan of action to resolve the problem. This is a very fancy way of saying just go and fix it. If it's a hardware problem, replace the defective part or correct the incorrect wiring. If it's a software problem, do what is necessary to resolve it and make the software work correctly. The fifth step is to verify full system functionality. The key word over here is full. Quite often when we solve a problem, we will ignore the fact that our solution may have caused another problem. We need to verify that everything is working correctly to make certain that it is indeed repaired. And the final step is to document the findings, actions, and outcomes. Now this is something that most of us seldom do, but it's a very good idea. After all, you could run into a similar problem down the road, and by having documentation as to what caused the original problem and what actions you took to resolve it, you could resolve the problem much quicker. And we'll apply these 6 steps in all of our troubleshooting efforts. So as you can see from the CompTIA method, troubleshooting can be broken down into a fairly methodical process. But one of the key parts of troubleshooting is your own knowledge, knowing how a device is supposed to work and knowing how it works internally. Those are critical to being able to troubleshoot. As a former bench technician, we used to get a lot of things in that were actually working just perfectly. They had nothing at all wrong with them. It was just simply that the individual who sent us the device either didn't know how to operate it correctly, or they were trying to use it for something that it was never designed for and therefore it couldn't do. So you need to know how your device works. Well, that you probably know because if it's a Raspberry Pi or an Arduino project, you're building it in order to do a specific thing. But you also need to know how the circuitry works and how the code works, how it really works. Now, if you're taking a project that you found on the internet or on YouTube and you're building it and you're just copying the code and just wiring things as per instructions and it doesn't work and you don't really know why you're hooking things up or why this code does what it does or why they use the specific statements they do, then you're not in a good position to troubleshoot it. You really need to know how it works internally. So if you are in that position, what you need to do is sit back and read the code, understand what it is supposed to do. Look at the hookup. Why are things hooked up the way they are? All of that will assist you in troubleshooting. So having said that, let's go on to our troubleshooting example. Now for our experiment, you're going to require an Arduino Uno, a linear potentiometer. I used a 10K pot, but any value of 5K upwards would suffice. A small servo motor, an SG90 is the best type to use for this. A couple of LEDs. I used a yellow one and a red one, but of course any 2 colors would work. 2 dropping resistors for those LEDs. I used 220 ohm resistors, but any value from 150 to 470 would work fine. And a separate power supply for the servo motor. Now it's critical that you don't power this from the Arduino. I used a 6-volt supply consisting of 4 AA batteries, as this is what the servo was actually rated to use. We begin by connecting one side of the potentiometer to the 5-volt output on the Arduino. The wiper of the pot is connected to the analog A0 input, and the other side of the potentiometer is connected to the Arduino's ground. Next, we connect pin 12 of the Arduino to one of the dropping resistors and then to the anode of the red LED. Pin 11 goes through a dropping resistor and is connected to the anode of the yellow LED. We then connect the ground to the cathode of both LEDs. Now we connect the ground of the servo motor to the negative side of the power supply. This is usually a brown wire on most small servos. The power, or red wire from the servo, is connected to the positive side of the servo power supply. And the servo control line, which is generally orange, is connected to pin 10 of the Arduino. Finally, we connect the ground of the Arduino to the negative side of the power supply. And this completes the wiring of our circuit. This is a sketch that we're going to be using for our demonstrations today, and it's a very simple sketch, really. We're going to start off by using the servo library and including it in our sketch. Now, the servo library is part of your Arduino IDE, so you won't need to download any external libraries. It's already there for you. Next, we create an object to represent our servo motor, and I'm going to call the object servo motor. The next thing is a variable that represents the position of the servo motor. Now, the servo motor can travel anywhere from 0 to 180 degrees, and it's going to be represented by an integer we call angle. We're also going to need an input for the potentiometer. I'm going to call that SRV control, and that's on A0 because our pot's connected to analog pin A0. We also define a couple of integers for the LEDs, so I got LED red on pin 12 and LED yellow on pin 11. Now, in the setup, we attach the servo motor to the pin on the Arduino that we're using. And so since we're using pin 10, we attach the pin 10. We also initialize the LEDs both as being outputs. And now we go into the loop. We start the loop off by reading the value from the servo control connected to A0 and assigning that to the angle variable. Now, that value is going to be a value from 0 to 1023 because the 10-bit analog to digital converter in the Arduino is going to give you that value. We need to map it to a value of 0 to 180, so we're going to use a map command to change that. Now we're going to use the LEDs. We're going to light one of the LEDs if the value is above 175. So we're going to check to see if the angle is greater than 175, and if it is, we're going to turn the red LED high to illuminate it. If it isn't, we're going to keep it off. We also want to light the yellow LED on the opposite end of travel if the value is below 5 degrees. So if the angle is less than 5, we're going to light the yellow LED and we're going to turn it off if the value is greater than 5. And then after that, we're going to write that angle to the servo motor. In order to move the motor into that position, we'll apply a very short delay of 5 milliseconds, and then we'll start the loop over. So again, this is a pretty simple sketch. So let's go and take a look at how it works right now with a fully working sketch, and then we'll go ahead and break it. So here's our test circuit, and you can see all the various components. Obviously my Arduino is over here, and on the solderless breadboard I've got the potentiometer mounted. I've got the two LEDs. You can sort of see them buried behind the wires. When they glow, you'll see them better. Here is my 6-volt supply for my servo motor, and here's the servo motor itself. Now on the solderless breadboard, I've taken these two supply rails at the top and used them for the 6 volts, and I've taken the two supply rails at the bottom and I have used them for the 5 volts from the Arduino. And the dropping resistors for the LED are probably a little difficult to see, but they're back over here. So this is running right now. I've loaded my sketch up to the Arduino, and as I move the motor, you can see the servo move. Now if I move to one extreme, you will see the yellow LED. So right now the value has dropped below 5 degrees. And if I move all the way up to the other extreme, you'll see that the red LED is illuminated, indicating I've gone above 175 degrees. And so there's really not much more to it. I can manipulate the servo. That seems to work. And as I go end to end, the indicators are telling me that I've reached the end of travel. And so this is our working circuit. Now let's go and see what happens when the circuit doesn't quite work the way we want it to. Now this is a flowchart that represents the test circuit that we've constructed. We start, of course, in the start box. And in the start, we load the servo library, we create an object for the servo, we define the LED pins, we define the potentiometer pin, and we create a couple of variables. Then we move into the setup. And in the setup, we attach the servo to the Arduino pin we defined, and we set the LEDs as outputs. Then we move down and read the potentiometer. With the value that we read from the pot, we rotate the motor to a specific position. And then we check that value in a decision box. That's this triangular box. If the value is greater than 175, then the red LED is illuminated and we go back up and read the pot again. If it isn't greater than 175, the decision box answer is no, and we move into another decision box where we check to see if the value is less than 5. If the value is less than 5, then we illuminate the yellow LED and go back up and read the pot again. If it is not less than 5, then we exit the box on the no side and go back and read the pot. The stages from read pot on are the loop in our program. So you can see how this flowchart corresponds to the code that we wrote. Well, now we've seen our simple test circuit and it seemed to work pretty well, so it is time to break it. Now I'm going to induce a problem into this circuit, and the problem I'm going to add to it is actually a fairly common problem. I've seen it before, I've even been guilty of it myself. And so let me go and just do something sneaky to this circuit. We'll run it again, see what isn't working, and then we'll see how we can troubleshoot the problem. Alright, well I've gone and done something nasty to our circuit over here, and at the moment it's not doing exactly what it should be doing. Now I'm going to move the pot, and as you can see, nothing is happening on my servo motor, so that's not a good thing. Now I do still have all the batteries in. I didn't just go and reverse one of the batteries to mess up the power supply, and I'll tell you right now the servo is still connected. I haven't changed any of its connections whatsoever. Now let's move the pot to one extreme of travel, and you'll notice that the LED is coming on, the yellow LED, which is the correct operation. And if I move up over here, you'll notice the red LED is coming on, so that's operating correctly. But the servo is not moving right now, and so there are a number of things that I'm going to need to test in order to determine why the servo isn't working. So let's go through the troubleshooting process right now. Well, as you've probably already surmised, I'm looking at a hardware problem in this particular example. After all, when I turn the potentiometer, I can see an LED illuminate when I get to one extreme, and I turn it all the way to the other end, and I can see the other LED illuminating. So we're obviously picking up the movements of the pot, and we are reading them enough to know which is the low end and which is the high end. But let's imagine for a moment that we didn't have those LEDs, so we had no indication that the pot was working. We were turning it and nothing is happening to our servo motor. We could be looking at hardware or software in this particular case. Obviously hardware could be a bad connection or a defective component like a defective pot or a defective servo motor. But we could also be looking at a software problem. Perhaps our logic is incorrect. Perhaps we're never actually driving the servo motor correctly, or perhaps we're not reading the value from the potentiometer in the first place. How do you determine if your problem is hardware or software? Well, one easy way to do that is through software by using the serial monitor. By using the serial monitor, you can place snippets inside your code in order to print out the value of variables to the monitor, and then you can go and move the pot, etc., and see if the values change the way that you think they should. And this is a very valuable technique for any troubleshooting. Now, if you're not working with an Arduino, if you're working with, let's say, a Raspberry Pi and Python, you can use the same technique by printing out to the console, and again printing out the value of specific variables to see if your code is operating the way that you should. So before we go and troubleshoot some hardware, let's go and take a look at the serial monitor with our circuit to make sure everything is working behind the scenes. Now, using the serial monitor is an excellent technique for troubleshooting code because you can place statements at various points in your code and examine the value of variables. Now, I've taken our sketch and I've added the serial monitor to it. So what I needed to do in the setup was set the serial monitor up with a serial.begin command, and you pass to it the speed that you want the monitor to go at. I'm using 9600 baud, but you can use a different speed providing you set your serial monitor to the corresponding speed. And then you simply place statements within your program. Now we only have one variable we're really interested in. So over here, after I've determined the value of angle, I print out the value of angle using a serial.println. And the println, as opposed to a print, will create a line feed after the statement. So everything will appear on a different line. If you just use print, they'll all appear one after another. And in some cases, that's what you want. But over here, we want each value on its own line. So I've already uploaded this to the Arduino. And so what we'll do is we'll go into our tools and we'll run our serial monitor. And as you can see, the serial monitor is displaying a value right now. Now notice down in the corner, I've got it set to 9600 baud, which matches the rate that I had specified in the serial begin statement. So now let's go and just turn the potentiometer and see what happens on our serial monitor. And as I turn it up, I'm getting values up to about 179, which is my maximum range. And as I turn it down, I'm going down to 0. So it does look like this statement is working. In fact, it looks like the code is working correctly. And if that's the case, then our problem is indeed a hardware issue. So now that we've confirmed our initial suspicion that this is a hardware problem, it's time to bring out some test equipment. Now, of course, there is a lot of test equipment you can purchase. Some electronic workshops have thousands and thousands of dollars of test equipment. I have test equipment like oscilloscopes and frequency counters and signal generators that you probably do not have, especially if you are starting out. And you don't need test equipment like that. Indeed, there is one piece of test equipment that you can buy that'll satisfy most of your needs, and it is this. It's a multimeter. Now, as its name implies, it's a meter that does a number of different things. It can measure voltage, it can measure resistance, this one can measure capacitance, it can check transistors, you can measure current with this, you can measure continuity. The thing that I'd use this for the most is measuring voltage and checking continuity. I use the other functions occasionally, but those are the two most common ones, and they're the only ones that we're going to need to troubleshoot the problem that we have right now. A multimeter is an essential piece of equipment for anyone experimenting with electronics, and they aren't expensive. This is like a $25 multimeter. There's a number of different types. Of course, you can spend hundreds and hundreds of dollars on a calibrated meter that has several digits, but you probably don't need that level of meter when you're just starting out. If you are already in possession of a multimeter, that's wonderful. In fact, I have a couple of multimeters, and there are times when I use more than one of them. But if you don't have one right now, just go and pick one up. They're very easy to find. You can get them on Amazon, you can get them on eBay. I got this at one of my local hardware stores. Now, there's another piece of test equipment you might want to consider adding to your arsenal that is also not very expensive, and it is this. This is a logic probe. Now, you may have seen me use this before. A logic probe certainly is not a substitute for an oscilloscope, but in a lot of cases it'll make do when you're not trying to make a measurement, but when you simply want to know, is something going high, is something going low, or is there a pulse over here? A logic probe is an ideal tool for that. Now, this probe lets you tell what the state of logic is that you're touching with it, both by lighting up a couple of LEDs and also making a rather irritating sound. And while that may be irritating, it's a useful thing because you don't always have your eyeballs on the probe, so you can just hear the results as you're poking around. So I'm going to show you how we can use both of these pieces of test equipment in order to troubleshoot the problem that we have with our little circuit. And so we brought out the test equipment to test our circuit. Now, the first thing we have here is a multimeter, and this multimeter is an auto-ranging multimeter, which is actually rather nice because all I need to do is select a function like AC volts or DC volts or ohms or capacitance, frequency, etc. And I don't need to worry about setting a range. I've got another multimeter over here I'll just show you, and this one is similar to that multimeter except it's not auto-ranging. So for example, for DC volts, volts, I would need to actually set the maximum range. It has a range of 200 millivolts, 2 volts, 20 volts, 200 volts, and 1000 volts. In the case of this circuit, I would probably set it for 20 because I'm dealing with 5 or 6 volts in this circuit right now, so that would be within range. The auto-ranging ones are a little easier to use, and they're not that much more expensive. Now, let's go and turn our meter to the DC volt position right now. And there's a couple of voltages we can measure. Obviously, we'd like to know if these batteries are working. If the batteries are dead, then that could be the reason that the circuit isn't working. And I've connected a couple of leads to the breadboard to facilitate that. It's a little hard to sometimes get the probe into the breadboard connections. So here's the ground, and here is the positive lead. And I've got 5.135 volts right now. And 5.135 volts is not bad. It should be around 6 volts, but these batteries are probably a little low. And the motor is connected as well too. It's probably drawing a slight bit of current, although not much because it's obviously not moving. Okay, the other voltage I can check is the 5 volts coming from the Arduino to make sure that that's working. And I've brought that out over here onto these connections, and the main reason for doing that, as you'll see soon, is for my logic probe. So let's just try to quickly check that voltage. 4.821, which is pretty close to the 5 volt logic that we need over here. So I believe that our voltages are correct. Now, another thing that you can do with a meter like this is check continuity. And you'll go into the ohms scale for that. Now, if I touch the leads together, of course, it should go down very close to 0 ohms, and it's 0 ohms. But what is useful on this meter and on many meters is that you can also do an actual continuity function. If I press this button here, first it goes to a diode test function, which is a very useful function as well. It lets you see the voltage drop across a diode and lets you see if that's working. This function is the continuity one, so if I put the leads together, I get that annoying beep sound, and while that may indeed be an annoying sound, it's very useful because then I can focus on where I've got the test leads without having to keep my eye on the meter. I can hear it when I have continuity. So I use that function a lot, especially when I'm soldering things, maybe some perf board, and trying to figure out if my connections are all good or if anything's shorted. I can use that. Now, I'm not going to go over the board with that, although if I would, I think I'd probably solve our problem, to be honest. But you can do that to check your connections. Just if you're not sure about a connection, place the meter on one end and the other. Take the power off of it in that particular case, and then go and check for continuity and make sure you've got all your connections correct. Now we'll put this aside now and look at our logic probe. Now, as I showed you, this is a logic probe. It's a very simple probe. It's got lights for high and low, as well as another one for pulse. You can also set it for different levels. I've got it set to TTL, which is transistor logic, and that's the type of logic that we generally use with these circuits. It's the 5 volt logic we're used to. Now, the pulse one is very useful. And we should be getting a pulse going out to this servo motor if the circuit is working. If it's not, we won't be. And that should be the orange lead down here. So I'm just going to try to touch that if I can. And as you see over here, I think I've got a bad connection there, you are getting a pulse over here. So indeed, we are getting a pulse. And you can also check this for high and low. Like if I go over here to where this LED connection is down here, it's low right now. If I bring it up, it goes high. And so you can check all the different logic levels you're getting out with this, and it's a lot cheaper, of course, than an oscilloscope. And in some ways, it's handier because you don't really need to know the actual level or the actual pulse width. You just simply know that a pulse is there, or that a level is high, a level is low. So it's a very useful piece of test equipment. And these are the two pieces of test equipment that if you haven't bought any test equipment, I believe you should buy them first. Definitely the multimeter first, but then consider a logic probe. With these two devices, you'll be able to do a great deal of troubleshooting. So let's see what we know about our problem right now. We know that when we turn the potentiometer, we are getting the two lights to light. The only issue is that the servo is not working right now. We also know that through software that the servo should be working because we're getting a different value as we turn the pot, which we should indeed be passing to the servo motor. And we've even determined with our logic probe that we are getting pulses sent out to the servo motor. So we might have a bad servo motor, and the way to find that out, the easiest way, would be to simply put another servo motor in there and see if it works. So if you have another servo, that would be a great way to do it. And that's an excellent troubleshooting technique in general, substitution. If you have another part, you can just put the part in and see if that fixes the problem. Quite often it's as simple as that. In this case it's not, and I'll tell you right now that our servo motor is perfectly fine. So what we are looking at is most likely a wiring error. Now let's go and take a look at the schematic right now and see what kind of a wiring error we could have in order to cause this problem. Now we could go through with our meter over here in continuity mode like this and buzz out every single connection, but that's rather tedious, and it's not really that necessary because we already know we're getting power connections from the Arduino. We know that the connections to the LEDs are obviously working, and the other connection to the servo seems to be working because we're getting pulses on it right now. So we must have some other wiring error right now. Our potentiometer and the analog side is obviously fine. Perhaps the servo isn't wired correctly, and we can go and double check our connections to make sure that we're going to power and ground and then to the servo control line. And those all seem to be correct. You can go through and check it yourself, but that actually seems to be correct. So what else could be missing over here? Well, the key to our problem right now is to know how this circuit works. And the way that the circuit works, it is of course sending pulses to a servo motor. But those pulses need to have a reference, and the reference is the ground. Now remember, we're using two different power supplies. This is supplying the servo, and the Arduino is supplying our logic circuit. And so those two grounds need to be connected together. Ground is actually a reference signal. It is called ground because traditionally we used to actually physically connect that to the earth ground. You would drive a stake into the ground and that would be the ground line. And indeed you will find that in your home there's a good chance that the ground lead on your power connection is connected to the cold water pipes that you have in your home. This is a typical arrangement, and the cold water pipes run underground, so they're indeed connected to earth ground. Well, we don't have to worry about earth ground right now, but we do need to know if our two grounds are connected together. So I've got the power disconnected right now, and I've got my meter in continuity mode. And this black lead here is the ground from my Arduino, and this green lead over here is the one that I brought out to test voltage. It is essentially the ground or the negative lead from the battery, and they should be connected together. But when I put this together, they are not connected together, and that seems to be the problem. I've neglected to connect the two grounds together. In this case, actually what I did is I sneakily took the ground wire and I put it in the wrong place. Naughty me. I will put it back, and we'll now check. And we do have continuity right now. And so I think we've solved our problem. Let's get rid of all these spurious leads because they're causing noise. Back to our original circuit, which we will power up. And it looks like it's working right now. And so our issue was we did not tie the ground of the two power supplies together. And so although these pulses were going to the servo, they had no reference. The servo's reference is the ground on this side. The reference from the Arduino is the ground on this side, and they need to be tied together. So that connection was omitted, and that is the problem with our circuit, which we have now succeeded in troubleshooting. And so we finished our first bout of troubleshooting, and as it turned out, we had a hardware problem. And I hope you can see how we determined that that was a hardware problem, just with some logic and common sense. So what I'm going to do right now is expand upon the code in our circuit. I'm going to keep the circuit the same, but I'm going to add some additional code so that we can flash the LEDs a few times before everything starts. And of course, I'm going to do something to it so that it doesn't work exactly correctly, and we will figure out how to troubleshoot that and how to get it working correctly. So let me go and write a bit of additional code, and then we will go and take a look at our next troubleshooting problem. Now for our next demonstration, I've enhanced the sketch that we've been using. What I wanted to do was I wanted to flash the LEDs when the sketch was first turned on, when the Arduino was first reset, in other words. And so I want to flash one of the LEDs 5 times, wait a second, and then flash the other LED 5 times, and then go into the sketch and have it operate the same way that it did before. And so in order to facilitate that, I've created a function that I called flash LED, and I'll show you that function. It's right at the end of my sketch. Now this is flash LED, which of course its purpose is to flash an LED. And it's got 3 input parameters. The first one is LED pin, and that is which LED do I want to flash? What pin on the Arduino is it connected to? The next integer is the flash num. How many times do I want the LED to flash? And the third one is flash delay. What is the delay in milliseconds between the on and the off period for the LED? And so we can take a look at the function itself, and basically what I've done is I've taken the blink sketch and I've placed it inside a for loop. And so I will flash it that number of times, the LED pin, and the delay on it, instead of specifying a fixed number, is flash delay. And so in order to use that function, I'm put it into my setup, because remember, I only want the LEDs to flash when the program starts. So something you want to only happen once, you put in the setup. Something you want to happen over and over again, you'll put that into the loop. So the setup is essentially the same as it was before, with the addition of the flash LED command. So I flash the LED, the red one, 5 times, and I leave a 500 millisecond delay between flashes. I then apply a 1 second delay over here, and then I go and flash the yellow LED 5 times at the same parameter, 500 milliseconds between flashes. And I could vary those parameters if I wanted to flash them a different number of times, or if I wanted to make the delay different between the 2 LEDs. And so now that you've seen this sketch, let's go and see if it actually works. Alright, so I've uploaded our sketch to the Arduino. I've temporarily disconnected the power because the sneaky problem that I induced into it is actually something that you're going to see once the circuit is started. So let's put some power on and see what happens. Now, as you recall, what is supposed to happen is I'm supposed to flash the red light 5 times, then the yellow light 5 times, and then we'll go into the sketch that we had before, where we simply can move the motor using the potentiometer and get the lights illuminating at the end of travel. So let's put some power on this. There we go. And our red light is starting to flash. And it's supposed to flash 5 times. It's flashing more than 5 times. In fact, it's still flashing. It won't stop flashing. And of course our potentiometer isn't working. All that is happening is the red light is flashing. Essentially what we've done is we've just built a different version of the blink sketch, it would look like. So obviously we have something wrong over here. And so let's go and see what we can do in order to figure out what that is. Now, I think it's fairly obvious that what we have here is a software problem. After all, we had a working circuit and we added some extra code to it, and now it is not doing exactly what we wanted it to do. However, don't overlook the fact that you could have more than one problem with the circuit. There could indeed be another hardware problem over here with the potentiometer or with the servo motor that we haven't seen, just because the code hasn't got to the point where we can test those things. But first we have to resolve the software issue with the code that we added. So likely the function that we created has an error in it, or the way we're calling this function may have an error, or the fact that we're calling it in the setup and not the loop may be part of the issue. So let's go and see how we can troubleshoot this as a software issue. Okay, let's try and troubleshoot our code. We'll go down into the setup where we call our flash LED, because this is likely where our problem is going to be. Now, one technique you can use when you're troubleshooting your code is to not run a specific line, and you can kind of remark the line out by just putting a couple of slashes in front of it. Now you'll notice this line has now simply become a comment. So the code will ignore this line completely, it'll do the delay, and it'll go to the yellow LED flash. So let's just see if there's something specific about the red LED that's causing our problem. We'll upload that to the Arduino. And now we see the yellow flash. And the yellow keeps flashing. So obviously this problem is not specific to the red LED. I didn't actually think it would be. And so let's go back into code and undo what we just did. And let's experiment now. Now this is the flash LED, and we're passing it the LED pin, which is LED red in this case, the number of times we want to flash, which is 5, and that's what it's not doing, and the delay of 500 milliseconds, and by the look of the flash it probably is 500. So this is where the problem seems to be. Let's just tell it 2 and see if that makes a difference. And we're flashing to red again. And it still keeps flashing. So obviously that number isn't making a difference. Let's go back into our code and change that back to what it originally was and go down to the flash LED function, which obviously is the source of our problem right now. Well, let's examine this function a little more closely. Now we have the parameters, the LED pin, the flash num, and the flash delay. We know that these two are working. We know LED pin is working because when we changed from red to yellow, it indeed flashed a different LED. And we're pretty sure flash delay is working. We could have added a longer delay to make certain that it changed, but it looks like it's about 500. And so it's flash num that is the problem. And over here we've got what actually happens. Now flash num is used over here. So for the integer equals 0 to the integer is less than or equal to flash num, we will go and execute this loop over here. And the loop is basically the blink sketch with all these parameters inside it. But there's actually something we are not doing over here. We forgot to increment. So after it finishes over here, it just keeps going on because the value of I is never going to be less than or equal to flash num. It's going to stay at 0 all the time. We're not incrementing I at all. And so let's do I to increment I. Put a space there to make it look nice. And now let's go and send that. And see what happens. That looks a little bit better, doesn't it? It does indeed. Okay, now that I've made my code fix, let's try this again. Now I've uploaded it again to the Arduino, and I'm going to give it a bit of power, and we'll see what happens. And so there goes our red light flashing again. And stopped. And now the yellow light is flashing again, so it looks like we've had some success over here. And it stopped. And now it seems that we can move our motor to the extremes and get the light. So it does look like it's fixed, although actually it's not 100% fixed. Let me reset this because the problem here is a bit subtle, but you may catch it. So remember what's supposed to happen. The red light's supposed to flash 5 times. Wait a second. The yellow light is supposed to flash 5 times. And then we'll be able to use the potentiometer like normal. So let's just reset this. There goes the red light. There goes the yellow light. But that's actually not correct. Did you see the problem? I'm going to reset it one more time, and this time I'll show you what the problem actually is. I'm going to count the flashes. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I wanted to light the flash 5 times. It's actually flashing 6 times. So it almost works, but we still have a slight code problem. Let's go in and see if we can figure out what's making it do this. Now the issue we're having obviously has to do with our flash LED function, so we can ignore the rest of the code and concentrate on that. Now one simple way of fixing it, of course, would just be changing these 5s into 4s, and since we know it's flashing one more time than we want it to, that would probably work. But it's not the best way to fix it, because the flash LED function, if it were working correctly, would be a useful function that we could reuse in some other code. So let's go and see if we can fix that. Now, let's take a look at flash LED. We take the LED pin, we know it's working with that, and the flash delay, we know it's working with that, and flash num it's sort of working with, but it's flashing one more time than we need it to. And so flash num is only used in this particular statement here at the beginning of the for loop. And so this has to be where our problem is. And if you think about it, that is the problem. It's going from I to 0 to I is less than or equal to flash num. And in this particular case, we're starting at 0. And so since we start at 0, we're counting 0, 1, 2, 3, 4, 5, as opposed to starting at 1. So there are 2 ways that we could fix that. One way would be to make I equal 1 at the beginning. Another way, and the way that I'm going to fix that, is to change the less than or equal to just a less than, because equal to will make it too large. If it's less than, that's fine because we are less than 5, which is a number we're passing. But if we say equal to, we also run the statement one more time because it will be equal to 5. And so in order to make this correct, I'm just going to take this out and I'm going to load that up and see what happens. Alright, I've uploaded our code change with the equal sign missing, and I'm just going to reset this so you can see what the results are. 1, 2, 3, 4, 5, and it stops. 1, 2, 3, 4, 5, it stops. And now we can move the motor and of course get the LEDs illuminating when we reach the end of travel. And so it appears we now have a working circuit thanks to our brilliant troubleshooting techniques. Now before we go today, I wanted to mention a few other things about troubleshooting. These are things that didn't really fit into any of the previous categories, but I think they are important to mention because sometimes when you check everything, it still doesn't seem to want to work and you're scratching your head. There are other reasons that things will not work. Now the first one is a software thing. Let's say that you are putting together a project from something you saw, perhaps from me, perhaps from another YouTube video or an article or something on GitHub, and the project involves a library which you downloaded and installed or you got off of the Arduino IDE library manager directly, and you put it all together and it just doesn't work and you don't understand. I mean, you've got the wiring double checked, triple checked, everything is fine, you've gone through all troubleshooting techniques, everything seems okay. The code that you've got is the code that you directly got off of GitHub or off of the article, so you know it should work. You even saw someone in a video make this work, and yet it doesn't work. Well, one of the problems could be if it's an older project that you're looking at, it might have used an older version of a library, and sometimes features in libraries get downgraded, and you may have installed the newest version of the library which has downgraded the feature and it's no longer available. So check version numbers of libraries. That can sometimes throw a little loop to you because everything seems fine, but the version number is the issue. Another issue is something that you run across when you're working with electronics and working with things that work with high frequencies. I've had a lot of people write me about the NRF24L01s, for example. Those are the little RF modules that you can buy for next to nothing and use with your Arduino or Raspberry Pi in order to make a wireless device. And they're great little modules, but they can be difficult to work with because they're RF modules. Now, radio frequencies are actually sensitive to things like the length of wires, the proximity of components, and a lot of times when you put something like that onto a solderless breadboard, the breadboard itself, the length of your jumper wires, you're working with a tuned RF circuit and it'll throw everything off. Sometimes you'll pick up power supply noise as well. Now in the case of the NRF24L01s, there's actually a pretty simple solution, and I showed it in the video that I did about those things, is that there is a little carrier board that you can buy. It's only cost about $1, and it has a voltage regulator on it to make the supply voltage good, because supply voltage for those things is quite often the problem. It also has a capacitor to decouple the power supply, and since it's on a printed circuit board, all of the wiring is very small and it's already been made for the NRF24L01, and I find most of the time you can just solve those problems just by using something like that. So keep that in mind if you're working with radio frequency circuits. Also audio circuits, you'll sometimes get funny noises and things like that in audio circuits at your breadboard, and again you're picking up external interference. Sometimes you can cut it down by putting in power supply capacitors, but sometimes you really just have to build your project either onto a printed circuit board or a perf board inside a shielded enclosure. These are the kind of things, again, that you can go through the troubleshooting chart and everything seems to work right, but it won't. A third one, and a final one that I want to mention, is one that I ran across about a year or two ago, and it was when I was doing a project for a DroneBot workshop video. It escapes me which project it was, but I remember the situation. There was an LED that was supposed to light, and it just would not light. So of course I checked my wiring. I had it connected to the correct pin. I checked my code. It seemed to be fine. I checked the LED itself. It wasn't put in backwards. I could take it out and I could put current across it and make it glow, and yet this didn't seem to work. Well, there was a fellow called Sherlock Holmes, a fictional character Sir Arthur Conan Doyle wrote about over 100 years ago that I'm sure we're all familiar with, and one of Sherlock's sayings was that when you eliminate all of the other possibilities, the remaining one, no matter how impossible it seems, is going to be the answer. And this was actually the case. It was the jumper wire. The jumper wire looked perfect, but inside there was a break on the jumper wire. And I took the wire out, an ohm meter across it. No, it was broken. Another jumper wire in the circuit was fixed. So little gotchas like that you got to watch out for, because they do happen in the real world. Your solderless breadboard too, if you've used it a lot, sometimes the pins don't make correct contact, and just moving it over a couple of spaces will solve your problem and also indicate that you probably should purchase a new solderless breadboard. So at any rate, I hope you enjoyed this video on troubleshooting. It's just sort of the tip of the iceberg. There is a lot of techniques that I haven't covered today, but I think this should get you started. And so the next time you're building a circuit and it doesn't quite work the way you want to, don't panic. Just do some basic logical troubleshooting techniques, and I'm sure you will make it work correctly, and you will also learn a lot more about your circuit at the end. So I hope you enjoyed the video. If you haven't subscribed to the channel, please do. I really love getting new subscribers. If you'd like to discuss some of this stuff, check out the DroneBotWorkshop.com forum at forum.dronebotworkshop.com, and there's a lot of great people on there having a lot of great discussions, and I would love to have you join us. And also check out the DroneBot Workshop website for all sorts of articles and projects. And so until the next time we meet, please take good care of yourself. I hope you can get your circuits working, and I will see you very soon here in the workshop. Goodbye for now.